This is Doc Nylund bringing you a video on the Lorentz Force, specifically on a current carrying wire. If you have not watched my video on the Lorentz Force on a moving charge, please watch that video first. In this video, I will begin by introducing the Lorentz Force on a current carrying wire specifically, and then apply the concept to a practice problem. This can be a tricky topic for students, so be sure to pay close attention and let's get started. In physics, the Lorentz force, which is sometimes called the magnetic force, falls under the umbrella of electromagnetism. It is a strange force because it only exists under certain conditions. The Lorentz force only affects charged particles, but they have to be moving across a magnetic field, not in the same direction as the magnetic field. Well, remember that current is simply a whole bunch of charges moving in the same direction. So if the Lorentz force acts on a single charge moving a certain way, it should also act on a current of charges moving in a certain way. So let's investigate further. Let's imagine that we have a magnetic field represented by capital B, and that it is pointing out of the page. Remember that anything pointing out of the page is represented by a circle with a dot inside, kind of like the front of an arrow coming towards you. So all 28 of the little arrows are representing the direction of our magnetic field. Now let's imagine there's a length of wire in our field that is carrying current to the left. Well, since the current is flowing across the magnetic field and not in the same direction as the magnetic field, the flowing charge in the wire will experience the Lorentz force. If the current had been moving out of or into the page, just like the field, the wire would not experience the Lorentz force. Now, since force is a vector, this leaves us with two questions. First, how much does the Lorentz force pull on the wire? And second, in what direction does the Lorentz force pull on the wire? Let's start with the magnitude. According to the Lorentz force formula we used in the previous video, we can actually derive an equivalent formula where the magnitude of the force is directly proportional to the current in the wire, the length of the wire, the strength of the magnetic field, and sine of the angle between the current's direction and the magnetic field's direction. Remember that the sine expression has the important job of making sure that there is no Lorentz force at 0 degrees and a maximum force at 90 degrees. Now let's look at the direction. Just as before, your right hand thumb always points in the direction of the motion, which in our case is the current, moving to the left. Next, point your right hand fingers in the direction of the field, which in our case is out of the screen. So with your thumb pointing to the left and your fingers pointing out towards yourself, I know this is kind of awkward, you should notice that your palm is facing upward. So that is the direction of the Lorentz force on our current, up. If you're wondering why the right hand rule applies here, remember that conventional current represents how positive charge would flow if it could. So just like how the right hand rule applies to only positive charges, it can also be used for conventional current, which is what we always use in physics. So if we look back on the original illustration, if the current is flowing to the left and the magnetic field is pointing out of the page, the Lorentz force on our wire is upward. Now let's look at a fairly difficult practice problem. Please pause the video and read the prompt. So the minute we hear levitate, we need to think static equilibrium. Or in other words, we need to balance the forces on the rod. We know that gravity is pulling downward on the rod, so my Lorentz force must be upward in order to achieve levitation. That is our starting point. Since the magnitude of the Lorentz force must be equal to the weight of the rod, we can set the two equal. After some substitution and solving, we find that the magnetic field strength would have to be 0.30 Tesla in order to levitate the rod. But what about the direction of the field? If we look back at the illustration, we can use the right-hand rule to find this direction. Remember, We point our right hand thumb in the direction of the current, which is to the right. At the same time, our right hand palm has to face the direction of the Lorentz force, which we know has to be up in order to make the rod levitate. What we should find is that our extended fingers point into the screen. In physics, this is called the negative z axis. So in conclusion, we have found that a magnetic field with a strength of 0.30 Tesla and directed into the page is needed to levitate our current carrying rod. Thank you for watching my video on the Lorentz force. I hope you find it helpful in your journey through electromagnetism. Please feel free to subscribe to my channel and follow me on social media.